Hey everybody, welcome to AFIT, welcome to Dayton, welcome to Wright-Patterson Air Force Base. Um, you have such an awesome opportunity coming up for the next 18 months or 3 years, if you chose that route. So I'm Major Joshua Hess, and today I just kind of want to take some time to talk about my research interests, talk about some of the work that we've done here, some of the great work that E&Y has done, and yeah, cover some possible thesis topics or areas of research that you may be interested in. Okay, so I'm just going to go ahead and share some slides, which is a phrase that we've heard a lot over the past few months, right? So adapting to the DL environment was pretty challenging at first, but I think we've got it under control. It's been interesting, right? Going from what AFIT really brings to the table in terms of DoD focused research to to bringing that to a home delivery content. But hey, strange times that we're in here, right? So yep, so got my slides up. I can see it over here, and so yeah, we'll just go ahead and we'll get started on this one. So a little bit about me at first. I'm from Southwest Virginia, which means I went to Virginia Tech, right? And did that in 2009. And you may hear another faculty member that has very similar research interests who also went to Virginia Tech around the same time frame. And we always joke that we're basically the same person because we may or may not be for that one. But yeah, so did an undergrad at Virginia Tech in AERO, came here as a direct accession. So for the direct accession lieutenants, if you have any questions about that process, I've been through it, and then did a master's in astronautical engineering, and then went over to NASIC for a little bit, space systems engineer, and got to deploy while I was over there. I was in NASIC LNO with the KAOC. That was pretty interesting, and also worked with the Weapons and Tactics Shop with the ACF sales part of the ISRD, right, the ISR division. And then I came back and I was like, man, you know what? Dayton's really great and AFIT's really great. So I said, I'm going to try for this faculty pipeline gig. And so I did that, got my PhD, did that in adaptive attitude estimation. Lots of really cool stuff there that still a lot of interest in. And yeah, so this is just sort of a summary of a lot of my research interests here, right? So starting from the top right, whether it's adaptive estimation, which we need to understand a little bit about estimation theory before we get into adaptive estimation. Optimal control in that bottom right, that's an example of actually doing neurocontrollers to approximate optimal control solutions. Cislunar, which there's a conversation for a different room, different environment in terms of the relevancy of cislunar trajectories. My bread and butter, what I'm really interested in is relative satellite motion, okay? And we'll talk about that in the next slide a lot. I'm also interested in really unique heuristic optimization techniques and differential games. They're pretty cool. It's not just about chess. And that's my cat, Whoops. He's got an Instagram page. You might be able to find him. He's pretty cool. I like the guy. He's really appreciated my presence around the house. Yeah, so single, no kids. I have a cat. Whoops is his name. He's pretty cool again. And I really believe in a work-life balance, which is honestly, that's something that I think we should focus on, coming up as we are in this DL environment. It's been a little tough maintaining that work-life balance, but we made it through. And my one recommendation, first off, is to have a schedule, right, and keep to that schedule and make time for yourself, make time for your friends, make time for your family, but definitely also make time for that research too while we're at it. So, what have I taught here? So I've taught a lot, mostly in the on the controls and dynamics side. So I typically teach the ACES 525 linear systems course in the fall, which is basically the x dot equals ax plus bu. Let me solve that every single way imaginable, and then realize doing it in state space is so much easier. MEC 633A, so that's a course that we developed last summer, right? We're currently in the second offering of that, but that is a class that's particularly focused on spacecraft, rendezvous, and proximity operations, and it's a really great class, and it's gotten a lot of positive feedback for that. And so if you're interested in satellite RPO, if you're interested in the orbital mechanics of one satellite, you're probably interested in the orbital mechanics of two satellites. So now let's figure out the relative orbital mechanics. It's pretty cool. I did the nonlinear controls class. That was pretty interesting. Currently, Major Zagaris is teaching that. I've taught for the past 4 offerings the optimal control class, right? So that has been a really great class to teach for that. And I think we've come a long way in terms of being able to solve some really tough problems. Then a couple of one-offs where some people were deployed, or I needed to step in. So I taught like theory of vibrations. I taught the nonlinear optimization course. I taught the reentry course that Major Bettinger teaches, and I may be teaching some of that coming up in the fall for a little bit. And then we did a pseudospectral methods class that was really great. And usually I get a chance to interact with you all twice a day during the short quarter review, teaching MATLAB, right? And doing the MATLAB review, that's the one class that's twice a day when we're doing it synchronously, and it meets, 5 days a week. And it's a really great opportunity to get to know you from the very beginning. And then what's really great is 18 months later is you go from asking what a for loop is, and now you're doing, hypersonic perturbation something, right? It's a really cool transformation to watch. One disclaimer is that I'm essentially PCSing soon, allegedly. That's what they keep saying. But there's definitely some nuances there in terms of requirements for the job, right? So that's still kind of up in the air, but I plan on staying adjunct faculty. So, there's still time and opportunities to interact with you all. This is stuff that I'm incredibly interested in, and I've devoted a lot of time. So it's going to be really hard to actually kind of leave behind, to be honest. So just want to put that disclaimer in there. Sad face, I've been here since 2009, other than a deployment, right? Which has been a very unique opportunity to be here. And I love the Dayton area. I think you're going to find a lot of awesome things to do here, even in this pandemic time, whether it's the bike trails or it's, the local food scene, the local, all the different scenes that you could imagine. It's great here. Big fan, especially the hiking. It's great. But yeah, so kind of moving on to a discussion here. Let's see if this video plays. It may or may not be exciting in terms of video. I'll post these slides, and if you want, there is the opportunity to possibly have a higher level discussion. And we can also, I have a distro D or an FOUO version of this, but we can have a higher level discussion as well once everything gets worked out in terms of clearances and everything like that, right? Being passed from your previous job to here. So spacecraft rendezvous and proximity operations. So that movie that's playing, that I'm going to stop playing in a second, is an example of something called natural motion circumnavigation. It's really just plotting the two inertial orbits that have a difference in eccentricity and the relative orbit that you kind of get a free circumnavigation, right? Naturally from that. So I'm gonna go ahead and pause that because I know how cool and distracting that might be. So I did my master's focused on deriving and trying to apply these things called relative orbital elements. And it's a classical sense based on the solution to the Kolesky-Wiltshire equations, which are these equations right here, okay? In that context, we try to apply those to they're based on a circular reference orbit, okay? I try to apply those to an eccentric reference orbit and also a reference orbit that's applied by the J2 gravitational perturbation. And so that worked out okay, right? And there's definitely room for improvement. But, in the congested, the words, space environment, rendezvous and proximity operations is becoming of increasing interest, right, and of increasing relevance. So, I'm into coming up with optimal strategies for a variety of problem sets. This relative orbit kind of cut off that variety of problem sets, but that's pretty much what it's going to say. Novel formation flying, RPO routines and models, right? So whether that's coming up with different types of NMC to teardrop type of transfers, I'm really interested in that, and coming up with metrics and ways to condense that and ways to visualize that. I've done some work with Major Bettinger on formation survivability, i.e. what happens to other spacecraft in the formation if there's a catastrophic event. Okay, and we've propagated debris in not only the CW frame, but he's done some additional work propagating that in the cislunar environment. From a nonlinear controls perspective, also interested in, hey, if I get this 2x1 natural motion, great, that's natural, but if I want to track a circle, I might need to pass in, that reference and actually come up with some type of nonlinear tracking for that. Coupled translational and rotational relative motion, that's a really hard problem because now we're doing the full 6 degrees of freedom, and there's different timescales on that one too, right? So there's the translational timescale, which could be, I'm doing this maneuver on the order of, hours, days, and then there's the rotational timescale, which is, hey, I'm doing this on the order of, 1 rev per minute. Okay, so two different timescales, and that makes that problem pretty tricky. I'm also interested in effects of reference orbit eccentricity, orbital perturbations, especially J2 on terms of the relative orbit. At LEO, at GEO, it makes a difference, but if we're looking at that effect, we're primarily looking at low Earth orbit and station keeping and J2 invariant orbits with respect to that. I've recently gotten into relative navigation, and that includes adaptive estimation for that, basically common filtering with a variety of hypotheses in the bank. And then initial relative orbit determination, right? So that's going to be, how do I, based on a series of measurements and recent research we've been doing, so range difference of arrival, right? Basically TDOA, but multiplied by the speed of light, and coming up with that relative initial state vector, that initial relative orbit from that. And there's a lot of work left to be done there. And actually, that's kind of interesting because you can turn that into a series of polynomial equations, which you may think, hey, those are just polynomials. Those are probably pretty easy to do. Turns out not so much, right? Turns out that's actually really hard to do. You end up getting like 64 solutions, and you have to disambiguate, and there's some interesting stuff there. And then, you know, some low velocity, high mass, or high velocity, low mass collisions, and how does the resulting debris field propagate, and especially how does that affect the formation for that. So these are just some examples on the right-hand side in terms of, you know, visualizing the relative orbit here, doing a transfer between two NMCs. This is an example of all the different sets and realizations of relative orbital motion that you could imagine here. And I've got up here the AFIT centennial. Maybe that should be gone, but we celebrated our centennial. Recently, and this is the slide deck basically from when I last presented this. So we'll keep that in there. So one of the things that you can do with the Kolesky-Wiltshire equations with relative satellite motion is we can do orbital differential games. Okay, so now in the context of differential game theory, here we're talking about two, and you assume that they're intelligent players, and that's an assumption that they're going to compete optimally. And the classic way to think about this is the homicidal chauffeur problem, right? Where you've got a chauffeur who, for some reason, is trying to run over a jogger. Okay, and the jogger is like, there's a chauffeur for some reason who's trying to run over me. I would like for that not to happen. And so the jogger wants to maximize the amount of time that it takes to capture. And the chauffeur, or the driver, wants to minimize the amount of time that it takes for that capture to occur. So you get what's called a mini-max solution or a saddle point solution. Okay, and that's in the context of a zero-sum differential game as well. So we've done some previous work where we looked at a pursuer, evader, defender. So we were doing a pursuer, evader, zero-sum differential game and having a defender intercept anywhere along that solution. We've done pursuit evasion, where we've done this really cool thing called the indirect heuristic method, right? Which is, we're taking a really, really hard two-sided optimal control problem and we're solving it with a a heuristic optimizer, right? Just based on some auxiliary relationships that we have to derive. But it's a really elegant solution, and we've applied that to the idea of a centric reference orbit, and also with different conditions where maybe at the end of it you're competing for the sun vector, where you're competing to match orbits and whatnot. And so these basically give you design floors and design ceilings, okay, where now you're saying, okay, if I am trying to capture somebody, if I'm on this Nash equilibrium and that player moves off that equilibrium, okay, I may be able to catch them sooner, okay, but right, in that context, that's not their optimal point, right? So this is a saddle point solution in this case. So they're pretty interesting because they do give you basically design floors and design ceilings for that. So that's really cool and all, because that assumes that you have perfect state information. So what's really interesting is now if you say, what happens if I have incomplete or asymmetric or imperfect information? And we've had a recent graduate that looked at this, and this plot at the bottom left is an example of, initial covariance, okay, and playing this pursuit evasion differential game and comparing the initial positions and the capture positions and looking at how the covariance changes over time, right? And looking at how actually, since this was from NMC to it basically occurred 180 degrees out of phase on the NMC, which was really interesting. And I think there's some mathematical foundation that we can do there. Also interested in applying some classical solution techniques, such as the Apollonius circle, right? So homicidal chauffeur, you were able to solve that geometrically, right? If you move some reference frames around. And I think, just like any good movie franchise, you got to take it to space, right? So now let's take the homicidal chauffeur and take it to space. And so on the right, on bottom right hand side, that's just an example of the pursuer, evader, defender that Captain Spindle did in his masters, who's part of the current class, where he applied cooperation strategies between the evader and the defender, I believe, with that one, and how the resulting cooperation strategy affected the trajectory. So pretty interesting. Lots and lots of relevance there to the current space environment, right? So something else I'm interested in is adaptive estimation. So basically, it's the idea of I am common filtering, I'm doing some type of filtering, I get a state estimate, and I get a covariance, and I get residuals. And I do some math with that stuff. And I get all of those estimates and residuals from different hypotheses. Okay, so a measurement goes into a bank of filters, and from that bank, you get a whole bunch of data. So now let's do some math, right, in terms of basically fitting these residuals and seeing where they lie on an n-dimensional Gaussian curve and things like that. So this is what my dissertation was focused on, okay? And there's a lot of different applications here that we could talk about, right? So on that top right, that was the Japanese Hitomi satellite. You know, it was either the situation where the moment inertia that it was using, it wasn't accounting for the solar panels being deployed or something similar to that. And it was the idea that we could probably apply these adaptive estimation techniques, taking in its angular velocity, taking in different measurements, and mapping that to a change in moment inertia. Okay, so as a student, you'd focus on publishing work that's related to the actual scenario creation, the different types of filters, the adaptive estimation scheme that would be going on, because you can have cooperation between your filters and between the filters in the bank, and the different types of measurements and how that all comes together. So that's pretty interesting. We did some work where we applied this to maneuver detection. Okay, so maneuver detection on orbit, right? Assuming that I can track a deputy satellite with either angles only or range and range rate with some type of sensor that's giving us that data. And we show that we can actually use adaptive estimation along with something called variable state dimension filtering and using a metric of something called a Mahalanobis distance, and actually going through, and we showed we can track those maneuvers and estimate those maneuvers. So that was pretty interesting with that. So this is sort of a top level topic because this is presented over Microsoft Teams, and everything here is unclassified. Okay, so we have a large, in my opinion, large orbital warfare research group, and this is honestly where I spend the majority of my time. Right, is working related to this group, and we call it the CSRA, the Center for Space Research and Assurance Orbital Warfare Research Group. We meet every Thursday at 3 o'clock on Teams, and we'll meet via other venues if we need to for that week to go to a FOUO level, or we go in some of us will need to go in person, right, to have actual level discussions, right. So in this context, it initially started out as OEM, orbital engagement maneuvers. It's since we've sort of assumed cislunar and a few other topics into this research portfolio, and it's the Orbital Warfare Research Group, right? So it's a really great group of people, and it's a great environment to be increasingly relevant and leading the way in terms of research. And part of that is development of a one-on-one game that we're calling Proxbox and Mazer, right? And I don't have a slide on that just because I was keeping these slides completely unclassified, but we can have a different discussion in terms of that. But it's basically a game that we developed here, thanks to a lot of work by this group spearheaded essentially by Cole George a couple of years ago. If you know him, he's the one who put the biggest effort into, say, the current look at the game, right? And there's been a lot of work after him in terms of Dax Linville, in terms of other folks who have worked on this game and made it a really great product. And if you take the RPO course, you'll get the opportunity to give us feedback on that game and try to hopefully help us improve that. But yeah, let me know if you're interested, or Dr. Cobb, or Major Segaris, or Lieutenant Colonel Johnson, or Lieutenant Colonel Little, or Mr. David Meyer. Those are kind of like the big names. Those are the main PIs. Hopefully, I'm not leaving anybody out that are working this orbital warfare research group. Okay, and yeah, there's a discussion for a much higher level, but we can kind of go to the cislunar topic, right? Because we've had a couple of recent theses that we're looking at that. Okay, so again, cislunar and beyond geo is a very increasingly relevant topic for a number of reasons. And when we were originally publishing this and talking about this, we're talking about, hey, provides rapid reconstitution, alternate mission design frameworks where we can use dynamical systems theory to find novel transfers that we may not have seen otherwise. So, some of the advantages that you have there, whether it's refueling, whether it's some kind of like logistical in situ utilization, space domain awareness, but then you get down to the technical challenges. What's one of them? The space domain awareness aspect of it, right? So down at the bottom is results from Josh Osman in his thesis, right? So I think this was about a year ago. We went through and we said, hey, what if I wanted to do a field optimal or time optimal transfer from periodic orbits about L1 or about L2 and go to GEO? And maybe I have some type of scientific experiment and I need to stay inside of a sun keep-in zone, or I need to stay out of a solar exclusion zone. So there's a lot of knobs you can turn there. So what you see right next to it, sort of in that middle plot, is a Pareto front, which tells you the design space that you can start to explore with this one. Also, my cat just came in, so hopefully everything's going to be okay. So sorry about that. Thanks for hanging on this far. So in that top right, there is Jacob Dahlke's work where we said, great, there are these things called heteroclinic and homoclinic connections, right? And so you can basically ride, let's say you can hop off an unstable manifold, right? Go in a direction of an unstable manifold and say you're in a quasi-periodic orbit about L1. And maybe you can find a stable manifold that's going into a quasi-periodic orbit or a DPO here, or a distant prograde orbit. And so if you can find a connection in the state space where an unstable manifold intersects with a stable manifold, that's called a heteroclinic connection. A homoclinic connection, you would have unstable connecting with unstable and a stable connecting with a stable, right, or intersecting. And so what we did is we went through and we found that heteroclinic connection. And then we were able to use that as an initial guess to something called GPOPs, which allowed us to find really fast minimum control solutions, at which case we used something called continuation, and we developed a similar Pareto front for these types of transfers. And that Pareto front actually went in some work by Alex Collins, where now he was doing a logistical sort of mixed integer optimization approach to this, right? Where he took the information from these Pareto fronts and went through and was able to come up with like a logistics architecture for cislunar ISRU there. So lots of work to do there. There's a lot of weird math though, right? Just a warning at first. So here's some of the students that I've advised, right? So in terms of advising, Team Hess has had a lot of success, a lot of really awesome work that's come out of this, and not just my students, a lot of really awesome work that we are doing here in ENY and as CSRA, right? It's amazing the dedication and just the amount of work ethic that everybody here has had. It's a great team. Back when we were coming in to work every day, I was so excited every single morning to wake up and to go and get to do some stuff that is just cutting edge, really exciting, and interacting with some amazing people. So I am kind of jealous of you all for starting this journey right now, actually, to be honest. And also in terms of doctoral committee members, right? So there's just been some great work here for this one. And I'm currently working, and so you can talk to Lieutenant Cecily Gu and Lieutenant Nate Enders, currently advising them. If you want to see what it's like to be on Team Hess, right, for that one, or just to get a feel for it, they're doing great things. They're doing a lot of AI applications, right? So Cecily's taking a sort of a neural network approach to trying to do control allocation. So we have a satellite simulator called SimSat, and it's got reaction wheels, it's got CMGs, it's got fans to simulate thrusters, and you could say it's over actuated, right? So how do you allocate that control? And so a lot of the work that she's doing is using a neural network to figure that out. Nate is doing some really awesome moment of inertia estimation using reinforcement learning that we just presented at a conference that was supposed to be in Lake Tahoe, but it was in this room, right, virtually. And so he's doing some awesome work. Everybody's doing some awesome work. This is a great place to be for that. And so here's just some, if you want to check it out, here's some recent publications and conference papers from 2019 and 2020 that kind of highlight some of the work that we've been doing. And again, it's a lot of awesome work that is definitely, you have a lot to look forward to. So in terms of a research summary, what do I do? I am a big fan of rendezvous and proximity operations. I find it fascinating. I find orbital mechanics challenging. So now we're taking the orbital mechanics for 2 satellites and we're doing a lot of stuff with them. So it's a hard problem, but it's so important to an ever increasingly contested space environment, right? Orbital engagement maneuvers. So that was sort of like the development of TTPs for those orbital engagement scenarios. That's how the whole orbital warfare thing kicked off, right? AIOCS, we didn't talk about that, but it's basically doing AI for operations in contested space. And so there is a movement to go from one-on-one to many-on-many that we can talk about, say, at a distro D level later on, and some of the specifics of that. And I have some interesting diagrams and potential scenarios. But yeah, so that's going to be a project with AFRL-RV that we've been doing. It's a multi-year project. And there's a lot of really cool applications there. Basically solving these differential games, but having the AI do it for us, because why not? Dynamical systems. So again, that's the cislunar. So when you see CR3P, that circularly restricted 3-body problem. And with dynamical systems theory, there is a lot of information there that you can exploit that you may not be able to just see if you're looking at this in terms of the 2-body problem. Okay, especially when it comes to those invariant manifolds, there's heteroclinic connections, right, where you can get really cheap transfers if you're willing to wait long enough. I did a little bit of work, and there's definitely some increasing interest in dynamic sensor tasking. So that's using information theory metrics to figure out the best ways to task particular sensors in given environments under a variety of scenarios for that one. So that's interesting. Interested in attitude determination and control. We can look at Cecily and Nate's work right now in terms of some of the stuff that we're doing there. Novel optimization techniques. So again, that's looking at those heuristic, right? So that's looking at particle swarm optimization, genetic algorithms, and so forth and so on. Hypersonic vehicle employment. I recently did some work with Lieutenant Colonel Combes, who left, but I believe there's some students following on the work in terms of using reinforcement learning, right, to train hypersonic vehicles to do a variety of things with that one. So there's a lot of work there. And then with adaptive estimation and satellite maneuver detection, also a lot of work there. So there's a lot of work, a lot of exciting work, and I think that you all have a really exciting 18 months or 3 years ahead to work on this. So yeah, there's my contact information. Again, I'm set to PCS sort of at the end of the year, but I'm staying adjunct. And this is stuff that I'm really excited about, and that I would love to work with you all on this, especially in the field of prox ops and optimal control, and further developing that and further pushing the boundaries in terms of what we can do. Right. I think we're in a really unique opportunity right now with the development of the Space Force, and with everything that we're doing here. We have limitless potential here right now, and I'm really excited about that. Also, this comic, really funny with that one. So yeah, feel free to send me a message on Teams, or send me an email. I'm pretty informal, in case you haven't noticed. So feel free to reach out if you want to talk about things, or if you just if you're interested in some of these topics and you're like, this guy says he's about the PCS, I don't trust that. I can help you find a committee member that would be helpful in doing this, right? So I think that we're a great team here, and we're here for you, right? So with that, I'm going to stop the recording, and I will see you around. So this is the Friday of Labor Day weekend. So I hope that if you watch this, I hope you have a great weekend, and I will see you all around. Take care.